Number of subsets introduction. So far we've been learning all about subsets, what they are, and what characteristics define them. Now, on this slide, we're shifting gears a little. Instead of identifying subsets, we're going to figure out how many subsets a set can actually have. Think about it. If I give you a set, can you quickly tell me how many different subsets it contains without having to list them all out? That's what we're going to learn to do. This idea of counting subsets is really important, not just within set theory itself, but also in other areas of math and even in computer science. You'll find it pops up in probability, combinatorics, and when you start thinking about things like data structures and algorithms. For now, to keep things manageable, we're going to concentrate on what we call finite sets. That just means sets that have a limited, countable number of elements. We'll deal with sets that have, say, 3, 5, or 10 elements, sets where you can actually count how many things are inside. We'll build up our understanding with these before potentially looking at more complex scenarios later on. So, let's move on to the next slide, where we'll start to see how we can actually calculate the number of subsets. Number of subsets, understanding the concept. So let's move on to understanding how we arrive at the formula for calculating the number of subsets. As we discussed in the previous slides, we know what subsets are. They're the collections of elements taken from a larger set. Now, we want to figure out a way to systematically count them. Let's consider a set, and we'll call it A, that contains n elements. Now, when we're building a subset, think about each individual element within that set A. For each element, we have a decision to make. Do we include it in our new subset, or do we exclude it? That's it, just two possibilities for each element. So, if we have n elements, and each element has two choices, include or exclude, to figure out the total number of possible subsets, we multiply the number of choices together for each element. That means we're multiplying 2 by itself n times. This leads us to a very neat and powerful formula. The number of subsets of a set with n elements is equal to 2 raised to the power of n, which we write as 2 to the power of n in mathematical terms. It's written as 2 raised to the power of n. Let's break down what n represents. N isn't the set itself, it's simply the number of elements that are in the set. We'll see this in action with some examples on the following slides, where we'll apply this formula to sets with 1, 2, and 3 elements to really solidify our understanding. This formula is the key takeaway, and we'll be using it a lot, so make sure you understand the logic behind it. Number of subsets, step-by-step explanation. So we've established that the number of subsets for a set with n elements is given by 2 raised to the power of n, or, as we write it, 2 to the power of n, but how does that formula actually work? It can seem a bit magical at first, just seeing that exponent appear. This slide is where we're going to unpack that a little bit. We're going to look at some specific examples, starting with very small sets, to really see why this formula holds true. We'll build our understanding step by step, and by the time we get to slightly larger sets, you'll see the pattern emerge. We'll start with a set containing just 1 element, then move to a set with 2 elements, and then 3. By carefully listing out all the subsets in each case, we can verify that the formula, 2 to the power of n, consistently gives us the correct answer. This will give us confidence in the formula and a solid understanding of where it comes from. In the following slides, we'll be doing exactly that, listing out the subsets and comparing the count to what the formula predicts. Don't worry if it seems obvious for these small sets. The goal is to build a foundation so you can apply this concept to more complex problems later on. We'll then move on to generalize this understanding and also discuss some common mistakes students make when dealing with subsets. Example 1, set with 1 element. Now let's consider a very simple set, which we'll call A. This set, A, contains just 1 element, which is A. So what are the subsets of A? Well, remember that the empty set, that's a set with nothing in it, and we denote it with this symbol, is always a subset of any set. So the empty set is one of our subsets. The other subset is the set A itself, containing just the element A. So we have the empty set and the set containing, that's it, there are only two subsets. Now let's check if our formula works. In this case, n, the number of elements in set A, is 1. So, according to our formula, the number of subsets should be 2 raised to the power of 1, which is simply 2. And as we just listed, we do indeed have two subsets. This confirms that our formula holds true even for the simplest of cases. Let's move on to our first example. As we discussed on the previous slides, we're trying to figure out how many subsets a set can have, and we've established the formula is 2 raised to the power of n, where n is the number of elements in the set. This is a good first step, and we'll build on this with slightly more complex examples in the following slides to really solidify our understanding. Example 2, set with 2 elements. Now on this slide, we have a set named B, and it contains 2 elements, x and y, so we can write it as B equals the set containing x and y. Let's list out all the possible subsets of this set B. Remember, a subset can contain any combination of elements from the original set, including no elements at all. So, the first subset is the empty set, which we denote as the symbol for the empty set. That's a set with nothing inside. Next, we can have a subset containing only the element x, which we write as the set containing x. Similarly, we can have a subset containing only the element y, or the set containing y. Finally, we can have the subset that contains both x and y, which is the set containing x and y. So, if we list them all out, we have the empty set, the set containing x, the set containing y, and the set containing both x and y. That gives us a total of 4 subsets. Now let's check if our formula holds true. Remember, the formula states that the number of subsets is equal to 2 raised to the power of n, where n is the number of elements in the set. In this case, our set B has 2 elements, so n equals 2. Therefore, 2 raised to the power of 2, which is written as 2 squared, is equal to 4. And as you can see, this matches the number of subsets we found by listing them out manually. This further confirms that our formula is correct and works consistently. We'll continue to build on this understanding with more examples in the following slides. Let's move on to our second example. As we discussed on the previous slides, we're trying to understand how the formula for calculating the number of subsets works. Example 3, set with 3 elements. Let's move on to our third example, and this one will really solidify our understanding. Here, we have a set C, and it contains 3 elements, P, Q, and R, so we can write it as C equals the set containing P, Q, and R. Now let's list out all the possible subsets of this set C. Remember, we need to include the empty set. That's a crucial first step. So we have the empty set, which we denote as the symbol for the empty set. Then, we have subsets containing just one element, the set containing P, the set containing Q, and the set containing R. Next, we move to subsets with 2 elements. We can have the set containing P and Q, the set containing P and R, and the set containing Q and R. Finally, we have the set containing all 3 elements, P, Q, and R. If we count all of these subsets, the empty set, the single element sets, the 2 element sets, and the set containing all 3 elements, we find that there are a total of 8 subsets. Now let's check if our formula holds true. We said the number of subsets is equal to 2 raised to the power of n, where n is the number of elements in the set. In this case, n is 3, because our set C has 3 elements. So, 2 to the power of 3 is 2 multiplied by itself 3 times. 2 times 2 times 2, which equals 8. As you can see, the formula 2, 3 equals 8, which perfectly matches the number of subsets we manually counted. This confirms the validity of our formula and demonstrates how it works even with a slightly larger set. This is a great step towards understanding how to apply this concept to more complex problems, which we'll explore further in the upcoming slides. Number of subsets generalization. Let's delve a little deeper into why this formula, 2 to the power of n, actually works. As we've seen in the previous examples with sets containing 1, 2, and 3 elements, the number of subsets consistently matched what this formula predicted. Now, think about it this way. For each element within our set, we have a choice to make when constructing a subset. We can either include that element in the subset, or we can exclude it. That's 2 possibilities for every single element. So, if our set has n elements, and remember, n represents the number of elements, not the set itself, then we have 2 choices for the first element, 2 choices for the second element, 2 choices for the third, and so on, all the way up to the nth element. To find the total number of different combinations we can make, and each of these combinations represents a unique subset, we multiply the number of choices together. That means we're multiplying 2 by itself n times. This is precisely what 2 to the power of n, or 2 raised to the power of n, represents. Essentially, this formula isn't just a rule to memorize. It's a direct consequence of the fact that each element contributes 2 possibilities to the creation of every possible subset. And as we'll see in the next slide, understanding this is key to solidifying your grasp of this important concept. Key takeaways. Let's recap what we've learned about the number of subsets. This slide, titled Key Takeaways, summarizes the most important points. Firstly, it states that the number of subsets of a finite set, remember, a finite set is one with a limited countable number of elements, with n elements is equal to 2 raised to the power of n, or, as we would say, 2 to the power of n. So, if a set has, say, 5 elements, it will have 2 to the power of 5, which is 32 subsets. We've seen this in action with our examples on the previous slides, haven't we? We verified this formula with sets containing 1, 2, and 3 elements. Now, why does this formula work? Well, the slide explains that it's derived from the fact that each element in the set has 2 possibilities when we're constructing a subset. It can either be included in the subset, or it can be excluded. Think of it like a yes or no decision for each element. Because we have 2 choices for each of the n elements, we multiply 2 by itself n times, which gives us 2 to the power of n. Finally, and this is important to remember, understanding this concept isn't just about set theory itself. It's crucial for solving a wider range of problems in areas like combinatorics, which deals with counting, and even in computer science. So, mastering this will really help you down the line. Now, on the next slide, we'll look at some common mistakes students make when dealing with subsets, so we can avoid those pitfalls. Common mistakes. Now, remember from our earlier discussion, a subset is a set formed from elements of another set. The empty set, which contains no elements, is a subset of every set. It's a bit counterintuitive, but it's a crucial part of the definition. So, when you're listing out all the subsets, always start with the empty set to make sure you don't miss it. This is especially easy to do when you're manually listing subsets, particularly with larger sets. Imagine you list x, y, and then later list y, x. Those are the same subset. To avoid this, always list your subsets in a consistent order. For example, always list the elements within each subset alphabetically, or from smallest to largest. This will help you visually identify and avoid duplicates. Remember, we've been working with sets that have a limited, countable number of elements. The formula we learned, that the number of subsets is 2 raised to the power of n, where n is the number of elements, works perfectly for these finite sets. But if you have a set with an infinite number of elements, things get much more complicated, and that formula doesn't directly apply. That's a topic for a more advanced course. This is a simple but important point. When we use the formula 2 to the power of n isn't the set a B, C. It's the count of how many elements are in the set. So, if you have a set with 3 elements, n would be 3. Let's move on to the final slide, where we discuss some common mistakes students often make when working with subsets. Paying attention to these will really help solidify your understanding. So, keep these common pitfalls in mind as you practice, and you'll be well on your way to mastering the concept of subsets. Are there any of these points you'd like me to explain in more detail?